The RSA algorithm was introduced in the year 1978 in a seminal paper by Rivest, Shamir, and Alderman. Over the years, as RSA became integral to secure communications, various vulnerabilities and attacks have emerged, underscoring the importance of understanding and implementing RSA correctly. Take a minute to find out what's wrong in this snippet. You may pause the video at this point. When you pass 1 as the public exponent, you've made the decryption of the ciphertext produced using this key trivial, and if the length of the message is less than the modulus itself, then no encryption takes place. In essence, the security is broken. This is something that actually happened at SaltStack in the year 2013. But to truly appreciate this fact, let's understand the RSA Cryptosystem in the next section. Our goal here is to understand the implementation of the RSA Cryptosystem, the various padding schemes, and the attacks that have surfaced over the years. By the end, you'd be equipped with enough understanding of the primitive that you no longer treat them as simple parameters and function calls, and would be able to understand the multi-security implications of the decisions you make. The year 1978 witnessed the birth of a new era in cryptography with the introduction of RSA Cryptosystem, named after its inventors Rivest, Shamir, and Alderman. This development provided a method for secure digital communication and laid the foundation for modern public key cryptography. The security of RSA relies on the difficulty of factoring large numbers, specifically the product of two large primes. In the next few sections, we'll witness that the RSA operations begins with selecting two large primes, P and Q, and then we compute the product of these two large numbers as n. The security of RSA relies heavily on the fact that while multiplying these two numbers is computationally straightforward, the factoring of the large result, this large composite number n, is considered infeasible for sufficiently large primes. To clear the air and to set the conventions for the discussion that is yet to come, it's important for us to understand these two primitives, OS to IP and IP to OS. The RSA expressions, that is the encryption and the decryption mechanism, works on integers. Yet the ciphertext that you see in most implementations are strings. In fact, the encryption block that we will feed to RSA in the coming few sections will also be concatenated strings. But RSA needs numbers, it needs integers to work. So here's how it happens. Suppose you want to encrypt the plain text n. This n is often represented as 0x or e in hex. Now this n is fed to a function called OS to IP, which is octet string to integer primitive. So this converts the string into its big endian integer representation. For our example n, the endian representation, big endian representation would be 78. Now, the RSA needed numbers to work on, so it will compute 78 raised to e, the public exponent that we choose, mod n. We'll go through the expressions in a while. Now, it produces a ciphertext which is also an integer. This ciphertext, the integer ciphertext, is fed to a function called IP2OS, which is integer primitive to octet string. This converts the big endian integer that you see here into its string representation, and that's the final ciphertext that you witness. In this example, the ciphertext would be C, and this function would take that ciphertext in as a parameter and convert it. to the ciphertext string representation. These conversions are guided by the formula that you see on your screen. The OS to IP conversion is guided by this formula, and the IP to OS conversion is guided by this formula. We will get back to the details of this construct of these expressions when we need them in the coming sections. You may also go find these under RFC 8017. For most parts of our discussion, we will consider a sample example to be already in integer format. Here. By now, you know how they were converted to integers in the first place. Now let's understand how the RSA cryptosystem works. It all begins with Bob, the receiver of a message. They want to receive a message, say, from Alice. And essentially, Bob wants a private key D and a public key. And in lieu of which, they have to make certain operations. To begin with, Bob needs to generate two large primes, P and Q. These large primes can be generated via a variety of ways, one of them being the Rabin-Miller primality testing. Now, once Bob has generated the two large primes, they want to calculate n, which is expressed as the product of these two large primes. Once Bob has n, they want to compute phi n, or the Euler's totient function. An Euler's totient function is guided by the formula the product of p minus 1 and q minus 1. Once this is done, Bob is ready to compute the public exponent E. And the public exponent is chosen such that it always lies between 1 and the phi n that we generated in the step above, with the Euler's totient function. And the public exponent E is always co-prime with the Euler's totient function, which means the GCD of E and phi n is always 1. Now Bob chooses computes rather the private exponent D, and the private exponent is chosen such that E times D is always congruent to 1 mod phi n that we calculated right now. In other words, D is the multiplicative inverse of E mod phi n. Now, Alice can easily collect the public exponent, N and E have been generated, and D remains with Bob. If Alice wants to send over a private text, a plain text M, they can simply raise it to the public exponent E mod N, where N was the public moduli, the public modulus. And this is the ciphertext. Alice can send over the ciphertext to Bob. And Bob, if they want to regain the original message, the plain text M, can use the formula C raised to D mod N. This works because C was M raised to E times T mod N. And we just witnessed that E times D is 1. So this essentially is the plain text M. And that is how Bob regains the plain text M that Alice wanted to send over. Fortunately, You don't have to worry about picking all the large primes, computing n, the Euler's Totient function, by yourself. In most modern cryptographic libraries, these operations have been abstracted into the function. So you don't have to worry about picking the large primes or deciding how to run the Rabin-Miller probability testing. These have been implemented with the libraries. What you do have to worry about is choosing a public exponent E, which is sufficiently large enough. And we stress on large enough public exponent because in the future sections we'll see that a low public exponent is often a security threat. Besides this, you also want to worry about the size of the key that you want to generate. And this is guided by n right over here. Remember, we generated two primes, the two large primes, right? So the result of this would be an integer of certain length. And the length of this integer in bits or bytes is the length of the key that we want to generate. So you want to pass the length itself and the private exponent. These are the two things that you will have to take care of. Let's see this in an example. We're using Python's cryptographic library, pyca cryptography, to generate a private key. So we'll say RSA dot generate private key, and it needs two parameters, the public exponent itself, which we'll select as 65537, which is sufficiently large, and the key size, which we'll say 2048 bytes. Now, we want to visualize all the numbers that we have just learned about. So we'll use a function called private numbers. Now, to see the first prime p, this is our first prime, the one that we generate, the function picked for us. It hid away all the complex details and abstracted the Rabin-Miller test and how it computed this large prime. But this number, in fact, is a large prime number. Similarly, the number q is also a large prime. Now we want to see the public numbers. Here we have e, the public exponent that we chose or provided to this function, which was 65537, and n, which was computed as the product of the two large primes p and q. This is n. Now let's also see the private exponent d, and this is the private exponent d. That's the multiplicative inverse of this number modulo 5. All right. This is how the private public key pairs are generated in RSA. And it is important to note over here the discussion that we did isn't exactly how these functions work. A lot has changed over the years. Some paddings have been introduced. The Euler's Totient function has been replaced by the Carmichael's function. And in the next few sections, we'll learn about these developments. We'll learn why the Euler's Totient function isn't always the best fit for us. And we'll understand why the Carmichael's function has been chosen over the years. In theory, the Euler's Totient function works fine for RSA. However, in practice, it can lead to unnecessarily large private exponents. Remember how we decrypted the ciphertext C. We compute C raised to D mod n. The Euler's Totient function slows down decryption or signing as a matter of fact because modular exponentiation complexity grows with the size of this D. The core issue here is modular exponentiation. The larger the exponent d, more number of operations are needed, making decryption and signing noticeably slow. To solve this, cryptographers switched to the Carmichael's function. Unlike Euler's Totient function, the Carmichael's function, which is often represented as lambda n, provides the smallest exponent that satisfies the RSA correctness, thereby reducing decryption time, having no security impact on the security assumptions that we made. Mathematically, the Carmichael's function is expressed as the LCM of p minus 1 and q minus 1. Now, by mathematics, we know that the LCM of two numbers, a and b, can also be expressed as, in terms of those two numbers, a multiplied by b over the GCD of those two numbers, a and b. We'll use this simple expression to correlate lambda n and phi n. Our lambda n is now the multiple of p minus 1 q minus 1 over GCD of p minus 1 q minus 1. You may observe that lambda n is lesser or equal to phi n because this part right over here, the numerator, is phi n. And lambda n is dividing the numerator phi n with a GCD of those two numbers, which is certainly smaller, or at max equal to phi n. Now, this means that lambda n provides the minimal exponent needed for RSA's correctness, whereas phi n may be larger. That still works, but isn't necessary. Now, for large primes, if we subtract 1, it doesn't make a significant difference. So p minus 1 and q minus 1 computed in phi n is almost equal to n. Now, since both of these are prime numbers, since p and q both were primes, by mathematics, we know that p minus 1 and q minus 1 will be even numbers. Since they will be even numbers, they each have a factor of 2. If those are the only common factors, which is often the case for random primes, then we can also express the LCM, the lambda n, as LCM of p minus 1 times p minus 1 and q minus 1, and each of them have a factor 2. So we can say it's almost approximately equal to phi n over 2. What this means is when you compute the private exponent as the modular inverse of a small number phi n versus the modulo lambda n, the range from which one can choose is roughly twice as large in the former case. For quick modular arithmetic, if you say a mod 3, the possible values of a is 0, 1, 2. But if you say a mod 2, the possible values are 0 and 1. This is what we are trying to get at. If we compute E inverse mod phi n, and if we compute E inverse mod lambda n, our claim is that this expression has a way better range, way bigger range, in fact, while this has a tighter bound, a tighter range, which is why we say that this would always yield a shorter D. A larger D means the decryption or signing, the modular exponentiation takes a significantly larger time. Now, this is free performance gain because we didn't actually modify any of the mathematical primitives of RSA. But by simply replacing phi n with lambda n, we are getting a performance benefit during decryption or the signing phase. This is termed as free performance gain. Textbook RSA in its raw form has two major weaknesses. First, it's deterministic, meaning the same message always produces the same ciphertext. An eavesdropper or an attacker or an adversary, say Eve, can guess or derive plaintext by exploiting the predictability of outputs. Since RSA encryption is a public operation, an attacker can encrypt likely messages and compare results to the target ciphertext. This is a trivial chosen plaintext attack. Besides this, RSA is also malleable. That means that its algebraic structure allows an attacker to manipulate the ciphertext in meaningful ways that could help them find out the plaintext. Let us analyze each of them in detail with a sample example. Since RSA encryption always produces the same output for the same input, an attacker can pre-compute likely plaintexts, encrypt them, and compare the results. If the message is small or predictable, it completely breaks the confidentiality. Let us see that with an example. In our example, we select the two large primes to be 3 and 11 respectively. We compute n, which turns out to be 33, and we compute phi n, which turns out to be 20. Now, we select the public exponent as 3. At this point, we have our public key pair. The public key is 33 and 3. Now, on Alice's part, she selects a plaintext M to be encrypted, and she says the plaintext is 4. Alice computes the ciphertext guided by the formula M raised to E mod N. We just computed the prior public key E and M, E and N. So we plug those in the formula and we say ciphertext is 4s to 3 mod 33. Compute that and we'll say the ciphertext is 31. Now, on Eve's part, Eve knows that whenever you could compute the ciphertext for 4, it will produce the same ciphertext. Whenever you compute the ciphertext for a message 3, it will compute the same ciphertext. Similarly, if you compute the ciphertext for 1, it would give you the same results. And this is what Eve will exploit. So Eve will pre-compute the ciphertext for a sample of images, for a sample of plain text. For 1, it would be 1. For 2, they'd compute the plain text as 8. For 3, they'd compute as 27. And for 4, they compute as 31. Note that E and N are public knowledge at this time. Now, once they have the given ciphertexts 31 and they have intercepted this 31, they can compare these two and say by backtracking that it was generated by the plaintext 4. So the plaintext that Alice chose must indeed be 4. This is the determinism exploit in RSA, in the textbook version of it. Now, RSA also suffers from a malleability exploit. And to demonstrate this, we'll use the RSA's multiplicative property. That is, multiplying two ciphertexts. encryption of M1 and encryption of M2 is just the same as multiplying their plain texts before and then encrypting it. This is the multiplicative property in RSA. Now, let us understand the setup of this exploit. Alice wants to send a message N to Bob. After computing all OS2 IP, we get, for a sample, plain text is 4. Now, Alice computes the RSA for the ciphertext for this one, and we say RSA computed for 4 gave us the value 31. Alice sends this ciphertext over to Bob. Eve intercepts this. Now, Eve chooses a multiplier, and this is a clever hack here. So Eve chooses a plain text to multiply, and they'd say the multiplier that Eve chose is 2. So now at this point, Eve knows E and N, so they could compute the ciphertext for 2. And that turns out to be 2 raised to 3 mod n, which is 8 in our sample example. Now, what Eve would do at this point is they would simply compute a C dash, a new ciphertext, which is the old ciphertext that they've intercepted, multiplied by the new ciphertext that they've computed, mod n. In our example, the ciphertext that was intercepted was 31, and multiply it with 8 and mod 33. That would give us ciphertext 17. This is the ciphertext that Eve has computed, the modified ciphertext. Now, in Malleability Exploit, we assume that the attacker or the adversary has the decryption oracle with them, or an access to it. So Eve will forward this new ciphertext to Bob because they have access to the decryption oracle, and Bob would assume that this came from Alice. Let's say there's no integrity check in between, and decrypt it for Eve. Once decrypted, we say the decrypted message came out as 8. And Bob knew what the multiplier was. The multiplier that Bob chose was 2. The multiplier that Eve chose was 2. So Eve now knows that the decrypted value was 8. The multiplier that Eve chose was 2. So the plain text must be the modified plain text divided by 2, which is 8 divided by 2, which is 4. This is exactly what Alice set out with. They wanted to send over plain text 4. This is how the malleability exploit works in RSA. It uses the RSA's multiplicative property. In this section, let us understand the low-exponent attacks. Historically, a small public exponent such as 3 or 17 was popular because it used to speed up the encryption or signature verification. But soon this turned out to be a security concern. For quick recap in modular arithmetic, if you compute the modulus of a number a mod say 2, the probable output that you would get is 0 and 1. What this means is that if a number is divided by 2, the most of the remainders that you would get is either 0 or at max a 1. You can't get a 2 out of this because we are already dividing it by 2, and 2 won't leave a remainder 2. All right, what this would mean is if you divide 13 mod 2. And you ask, what remainder does 2 leave when it divides 13? The answer is 1. But if you do the same thing in 2 modulus 15, you ask yourself the question, what remainder does 13 leave when it divides 2? And the answer is 2 itself. How this relates to RSA is this. When RSA uses a small public exponent, say e is equals to 3, then the plain text is very short, so short that m raised to 3 is less than the modulus n. And this encryption does not essentially wrap around. It does not wrap around this modulo. What that would mean is the modulus is so small that m raised to 3 modulo n is m raised to 3 itself. Now, let's assume in a sample example, we choose the plain text m is 5. We assume or we choose n to be a 4096 bit length number. What that would mean is n is really large, say 2, 5, 5, 1, some numbers, and 7, 2, which is very large as compared to m raised to 3. So when we compute ciphertext, we'd say m raised to 3 mod n. The public exponent that we choose is 3. So it's 5 raised to 3 mod this large number, 2, 5, 5, 1, some huge numbers in between, and then 72. What that would mean is 5 raised to 3, which is 125, will not wrap around this large public modulus. And Eve, if they want to intercept this, if they can intercept the ciphertext C, they can simply compute the cube root of this ciphertext, because public exponent is a public knowledge at this point, and they could get the plaintext 5. This shows that if M is small enough, the ciphertext leaks the plaintext when E is low. That is the threat of using a low public exponent. In the following section, we'll take a look at a special type of low exponent attack called the Håstad's broadcast attack. And Håstad's broadcast attack utilizes a special construct of the Chinese remainder theorem, CRT. To understand how this construct spawns into action, you may want to watch the associated video that pops on your screen. The link to this video will also be available in the description section. Håstad's broadcast attack is a type of low exponent attack where the exponent e, the public exponent, is usually chosen as 3 or some other low value. For a quick recap, in the RSA Cryptosystem, if we want to encrypt a message, we compute C, which is the ciphertext, is m raised to e mod n. Here, e is the public exponent, and e and n is the private public key. Now, historically, this value of public exponent was chosen as 3 or any other low value because that helped increase the performance. In the year 1985, John Håstad highlighted the broadcast attack, which illustrates the dangers of using a low exponent, it's just 3. Let us understand the setup of this attack. We have Alice over here, the sender of a message. She wants to send a message M to 3 different recipients, Bob, Carol, and Dave. It's basically a broadcast to 3 different recipients. Now, Alice chooses the modulus N1 for Bob, N2 for Carol and N3 for Dave. And all of these are relatively coprime. Now, the ciphertext C1 is computed as M3, M raised to 3, because Alice shows the public exponent to be 3 mod N sub 1. For Carol, the ciphertext is M raised to 3 mod N2. And for Dave, the ciphertext is M raised to 3 mod N sub 3. Now at this point, the channel is insecure, and Eve is able to intercept all of these ciphertexts through one or the other mechanisms, such as man-in-the-middle attack. The channel itself is insecure, and the ciphertext can be intercepted by Eve. So Eve intercepts all these three ciphertexts. At this point, Eve has C1, C2, C3. Let us also recollect that the public exponent and the moduli itself are also public knowledge. What's not a public knowledge is M3, M raised 3 rather, because E was 3 and the chosen message was N. Håstad proved that Eve, or the adversary, can reconstruct M raised to 3, and then to get the ciphertext or the plain text itself, they compute the cube root of this computed X. Even the adversary can reconstruct this plain text even though they do not have access to M, or they don't know M3 as a matter of fact, M raised to 3, but they can recompute M raised to 3 and thus take the cube root and get the original message M back. This was the threat of using a low exponent in RSA encryption. Let's dive into the mathematics of it up next. To begin with, we are given three ciphertexts, or rather, Alice computes three different ciphertexts. CB, which is sent to Bob, CC, which is sent to Carol, and C sub D, which is sent to Dave. In all of these, Alice decides to choose the public exponent as 3. The moduli that Alice uses for each of this computation are NB, NC, and ND respectively, which is relatively coprime, or the GCD of NB and NC is 1. Similarly for the other two pairs. Now, we'll take a sample numbers for our example. We'll say the public moduli that was used for the computation of ciphertext sent to Bob was 187. The one used for Carol was 115, and the one used for Dave was 87. At this point, let's compute the ciphertext that Alice calculates for each of these recipients. Alice chooses M to be 42, and the public exponent is 3. This is in Alice's part. Again, in RSA, we compute the ciphertext as M raised to E mod N, in this case Ni, and this is what we are doing. So for Bob, it's 42 raised to 3 mod 187, because we chose the modulus to be 187, and it gave us the result 36. For C sub C, the ciphertext is 28, and for C sub D, the ciphertext is 51. These are the ones sent to Bob, Carol, and Dave. respectively. Now, on Eve's part, Eve now has access to E, NIs, and C1, C2, C3 because they have intercepted these ciphertexts. Now, they can construct N, which is the product of all these moduli, and it comes to this large number. Then Eve will calculate the Yi's, or in this notation, we'll call it the Ni's. For NB, it is N over N sub B, which was this large number that we just calculated over NB. And we get a number 10,005. Similarly, we calculate this for NC, this number over NC itself, and we get a number, the NC component of our equation. Similarly, for ND, we get a different number. Now, Eve has to construct ZBs, which was the modular inverse of NBs, or the NIs that we just calculated. Again, in certain textbooks, we have different representations and we want to know all of these. So ZBs could also be represented as MB, NC, and MD respectively. Again, they were modular inverses of the things that we calculated right before. So ZB is the modular inverse of NB modulo NB. ZC is the modular inverse of NC mod NC. And ZD is the modular inverse of capital ND mod ND. Now, we can calculate these inverses using the extended Euclidean algorithm. And once we have it, we have those values as 2, 49, and 49 by coincidence. MBs and MC are MD and NC are 49 by coincidence. The same values. At this point, Alice, Eve has everything they need to plug in the formula AI, YI, ZI, or to reconstruct or to know the other expression, we say CI, NI, and MI. These are just different notations for the same things. Now, at this point, Eve is ready to plug this in. They know the value of CVs, NBs, and MBs, CIs, NIs, and MIs rather. Now, Eve can simply plug those values in. We have calculated this right now. And get this huge number. They have to calculate the modulus of this number, so it's within the range of this. And after doing a mod operation, the final ciphertext or the clubbed message is this. This is M cube itself. If we calculate the cube root of this number, we get 42, which was what Alice sent out with. This is what Alice started with. Alice encrypted 42 itself. And Eve is able to reconstruct this, even without knowing any of the major data such as M, Q, or M. The only thing in possession of Eve were N, E, which was public information by that time, and the intercepted ciphertexts. And they can compute this. This is only possible for a low exponent, and that was the threat of a low exponent attack. And that is how the Chinese remainder theorem plays in the Håstad broadcast attack. In the next few sections, we'll take a look at the various padding schemes in RSA. These are defined in the public key cryptography standards. PKCS 1 version 1.1 to version 1.3 were published in the year 1991, though it was only privately distributed. PKCS 1 version 1.5 made its first public appearance in the year 1993, and it was republished as RFC 2313. In the year 1998, version 2.0 surfaced, and that introduced RSA OAEP. In the year 2002, version 2.1 came out, and that published the PSS encryption scheme, or signature verification scheme. And the latest one that we see today is version 2.2, which was published into the year 2012. And this is what we see in RFC 8017. We'll dive into each of these schemes as and when they have been published, and the various attacks as and when they have occurred. Let's start with PKCS 1 version 1.5. In PKCS 1 version 1.5, every RSA encrypted message is wrapped inside a special encryption block called EBE. This block ensures that the raw message is both of the right size for RSA and is padded in the right way that it's hard to tamper with. Let's understand what this block is made of. Here, 00 or the leading 0 byte is always at the front. This is by construct. It ensures that the concatenated string is converted to a big engine using OS2IP formula. The value is always less than RSA modulus. That is, we don't end up with a number too large for RSA to handle. The next block that we see here is BT, or the block type. This tells us the type of padding being used. The standard defines three possible values: 0, 1, 0, 0, and 0, 2 to support different operations. For example, 0, 1 and 0, 0 are used for private key operations such as digital signature schemes. 0, 2 is used for public key operations. For encryption under PKCS 1 version 1.5, this BT, or the block type, is always 0, 2. This label basically says that this is an encryption block and not something else. Now, the next block that we see is the padding string PS. This string is a non-zero, and I stress non-zero, random bytes. This is crucial for security because this block introduces randomness into each encryption. If the same message is encrypted multiple times, these random bytes ensure that the ciphertext looks different, foiling many simple attacks that rely on simple seeing repeated patterns. The next octet that you see here, 00, is called the delimiter. This single 0 byte marks the end of the padding. Remember, the padding is a non-zero byte, so the decryption can never confuse between the padding string and the delimiter. During decryption, this helps the recipient quickly find or identify where the padding stops and where the real message begins. Finally, we have the actual data that we want to protect, M. Once the recipient has verified the padding, they know exactly where to find this message. This mechanism helps solve the deterministic issue in naive RSA. In the next sections, let's understand the mathematics involved in PKCS1 version 1.5 padding and its security implication. In PKCS1 version 1.5, we use K to represent the length of RSA modulus N in bytes. For example, if you have a 1024-bit RSA key, then the RSA modulus N is a 1024-bit number. Since there are 8 bits in a byte, if your RSA modulus is L bits long, then you can compute this K guided by the formula L over 8, the seal of L over 8, which is 1024 over 8, which is 128 bytes. The total length of the encryption block will be equal to this key length K in bytes. Now, here the length of the data shall not exceed K minus 11 octets. Since this 11 octets is consumed by the block 00, 02, PS, which is the padding string, and again 00, which is the delimiter. Now, this limitation guarantees that the length of the padding string is at least 8 bits long, or 8 octets long, which means that PS, the length of PS, is K minus the length of M minus 3, these 3 blocks, which is 8 octets long. Now, this is a security condition in PKCS1 version 1.5. Now, RSA doesn't directly operate on bytes, as we have already previously seen this. Now, the padded string is ready to be converted to its integer form, guided by the octet string to integer primitive, the OS2IP formula. Let's pick 3 arbitrary non-zero bytes for the padding string PS. Let's say the 3 bytes that we pick are in hex A3, 5F, and C2. Remember, these are in hex, the hexadecimal representation of it. And let's say the message that we want to encrypt is hi. So we want to find the ASCII of hi in hex, and that is for H, it's 48 in hex, and for I, it's 69. This is the message here. And that is the padding string, the randomized padding string in the encryption block itself. And this right here is the delimiter. Now, we can simply plug these into the OS2IP formula to convert this into an integer primitive, x. And upon using that, or upon expanding that, we get this. Here, 00, the first byte, is multiplied with 256 raised to 7, and 069 69 was multiplied with 256 raised to the power 1. This was I, and this is 1. There's an interesting observation in the application of this formula. Because the first 2 bytes are always fixed 00 and 02. The integer x has a known lower bound. The contribution of the first 2 bytes is this. The first block 0 is multiplied by 256 raised to the power 7, and the second block 2 is multiplied by 256 raised to 6, which is in fact 2 raised to 2 times 256 raised to 6. Now, all of the remaining blocks have a power less than 6. 5, 4, 3, 2, 1, and 0, which is 1 itself. What this means is the length or the higher upper bound of this string S can never cross 2 times this number. For simplicity, let's call this number B, as many conventions call it. So we'll say that the length upper bound of the string S can never cross 2B because the value that is added after this is always less than 256 itself, 256 raised to 2 power 6, because the powers are less. What that would mean is that this number could be, the x that we calculated, could be at minimum 2 times b, or at max 3 times b. This whole thing combined could at max reach 256 times 6, but never 256 equal to 256 times 6, 256 raised to the power 6. This is the range that we see here. To sum up our discussion, the rest of the block that you see here, the delimiter, the padding string, and the plain text, adds some value that is at least this and at most just less than this value. Since the byte is fixed, it cannot be greater than this value. This is the range of the plain text, or the encrypted block. This property that makes the range predictable paved the way for the Bleichenbacher attack, which is also known as the padding oracle attack. If a system reveals whether a decryption block is correctly padded, an attacker can correctly systematically probe the ciphertext and narrow it down to the plain text, because the attacker knows that the message lies within this range. In the next section, let's take a detailed look at the Bleichenbacher attack and understand how the exploit works. In the year 1998, Daniel Bleichenbacher demonstrated an adaptive chosen ciphertext attack against RSA PKCS version 1.5 padding. The Bleichenbacher attack, also dubbed as the million messages attack, demonstrated that if an attacker has access to an oracle that tells whether the submitted ciphertext decrypts to a properly padded plain text, that is, whether the PKCS1 version 1.5 formatting is correct, the attacker can gradually recover the full plain text. Let's break down how the attack works. First, Eve needs an oracle. This attack assumes that the attacker or Eve can query a system such as an SSL or TLS server and find out if the given ciphertext is PKCS1 version 1.5 confirmed. In the 1998 paper, Daniel Bleichenbacher exploited the fact that TLS server, when presented with an improperly padded pre-master secret, would respond with a specific alert if the padding was wrong. Essentially, the server acted as an oracle and would simply tell the attacker if the padding was okay or if the padding had an error. Note that the oracle does not reveal plain text. It only reveals a single bit of information at a time. Either it's valid padding or it's an invalid padding. This might seem harmless, but Bleichenbacher showed that it was enough to recover the plain text. Now, Eve makes use of the homomorphic property of RSA that we discussed in the previous sections. That is, if Eve chooses a multiplier 3, then they can compute 3 raised to E times the intercepted ciphertext. Now, this would be same as saying 3 raised to E times M raised to E. And that would be same as 3 times M raised to E mod M. Now, if the decryption oracle deciphers this for Eve, they're left with 3 times M. And Eve can now simply find out the M because they were the one who chose the multiplier. Now, Eve can easily find if if the ciphertext was conformant to the PKCS1 standard using the oracle, because they have access to it. But the challenge here is that there are so many values between 2b and 3b that we don't know if multiplying a certain value, say 3, to the intercepted ciphertext will return a correct ciphertext or not. This is the interesting part that Daniel Bleichenbacher came up with. In repeated attempts or loops, Bleichenbacher proved that we can narrow down the range of this text, and we can ultimately find an, our value for this narrowed down range, which is equal to the plain text m. To completely understand how this attack works, let's dive into the mathematics behind this attack and take a look at a sample. Eve had one wide interval A to B that contains 2B inclusive and 3B not inclusive. Remember, Eve needs to find a multiplier, SI, that when multiplied with the interceptor ciphertext would result in a conformant ciphertext. In each iteration, Eve tries increasing the value of S, starting from a certain minimum, until the oracle returns yes or padding OK. Suppose this happens for a ciphertext C dash, C0 times S raised to E, and S is ciphertext, S is the chosen multiplier that Eve chose. Given this feedback, Eve will now know that M times S lies in this range, that is, lies within 2B to 3B. This congruence implies that there exists an R that results in this value also being in the same range, 2B to 3B. Now, if we rearrange this constraint on M, we get a constraint on M that is 2B plus R times N over SI. So M should be strictly greater than or equal to this value, and it should be lesser than 3B plus R times N over SI. The attacker's goal is to find one or more such SI values that will allow us to narrow down the range or the interval in which M lies. The attack, as per Bleichenbacher's algorithm, instructs the attacker to start with a value that's at least the seal of N over 3B. For a modulus that's represented, that the modulus representing in K is equals to 3 bytes, let's define a few sample numbers for our example. We select the modulus n as 67591. We select the public exponent e as 3. The plaintext that we want to recover is 600. And now let's find the range. For that, we need to find the value of b. So the value of b turns out to be 2656, and the range turns out to be 512 inclusive and 678 exclusive. Now, remember that this value of b was taken such that the modulus represented in k is 3 bytes. A properly padded plaintext, when interpreted in integer, must lie in this interval. That is, must lie in the interval 512 inclusive to 768 exclusive. When we compute a ciphertext, we get this value as a ciphertext. Now, the attacker can only see the ciphertext and has access to the oracle that tells them whether the decrypted value, when interpreted as an integer, is correctly padded or not. That is, if it lies in this range. Now, for our numbers, we can calculate the minimum value of S as n over 3b, which is 67591 over 768, which is approximately 88. Now, the only integer here is 88, so we'll start with the value 88 as we've taken the seal of it. Now, The attacker queries the oracle with manipulated ciphertext. They try all various values of S, such as 88, 89, 90, and so on, until the oracle says valid. Yes, that is the decrypted plain text lies in the given range, in our valid range. Now, after trying several values, suppose the attacker finds that the oracle responds valid for S is equals to 339. Now, we try to find a valid R. We need an integer R such that this expression lies in the range 512 to 768. Let's test R is equals to 3. For R is equals to 3, this expression is evaluated as 627, which is indeed in our given range. That means R is equals to 3 and S is 339 is a valid combination for our attack. Now, the inequality that resulted in the valid padding was this. We can rearrange the bounds on M and we get 2b plus 3n. That is what this should be greater than, and this is what this should be less than. Now, if we divide this by S, we get this expression, and the value of S that we chose was 339. If we plug in our values, we can find the lower bound and the upper bound. So the lower bound that we find in our example is this. We plug in all the values and compute the lower bound as 599.66 and the upper bound as 600.41, which means that M must lie between 599.66 and 600.41. There's only one such integer that can lie in this range, which is M is 600, and that is how we've recovered the plain text using the Bleichenbachers. For our sample example, we didn't need a lot of iterations, but in a value where the modulus is large, in a real world example, you'd have to go through all of this loop in a couple of times and find the range in which M is sampled out to be one value. There's only one possible value it can result in, and that's this plain text that you can find out using the Bleichenbacher's algorithm. By the end of 1995, Belair and Rogaway proposed optimal asymmetric encryption padding, or OAEP, with the goal of achieving provable security. This padding aimed to make RSA encryption not just resistant to passive attacks, but also to adaptive chosen ciphertext attacks. In other words, even if attacker can trick a system into decrypting chosen ciphertext, they should learn nothing useful about the plain text. OAEP was subsequently standardized in PKCS 1 version 2.0 in the year 1998 and was republished as RFC 2437. Compared to PKCS 1 version 1.5, OAEP has a more complex encoding that uses hash functions and mask generating functions, MGF, to thoroughly randomize the plaintext before RSA encryption, thus providing stronger guarantees. OAEP's design can be viewed as a two-layered 5-step network using a random seed. It takes input message and randomizes it in a way that it's reversible only with the correct seed. The scheme was proven plaintext aware in the random oracle model, which means that an adversary, say Eve, cannot concoct a valid ciphertext without knowing the corresponding plaintext. If an attacker tries to forge or tamper with the ciphertext, they almost surely never will produce a valid padding, and that will be rejected. This property counters directly the padding oracle attacks. Unlike PKCS1 version 1.5, which lacked a formal proof, OEP comes with a proof sketch that breaking RSA OEP is just as hard as breaking the mathematics behind RSA itself. On a higher level, let's try to understand the setup of this encrypt padding scheme. We'll create a data block which will contain a hash. We'll soon find out what lhash means. It will also contain a padding string, a delimiter, and the message M. It will then be masked by a mask that is created by this MGF function. A seed will be chosen, which will be random again, and that seed will also be masked by this masked out data that we just generated. And this mask will be generated by the second MGF function. The mask that we generated in this at the end of this row will be called masked data block, and the seed that we just masked is called the masked seed. The encrypted message will always begin with a 00 by construct. OAEP drastically reduces the risk of any padding at Oracle. An attacker can no longer easily find ciphertext slips through the padding check, except by brute force. And in that case, the probability of success would be 1 over 2 raised to hlen times 8. Since at this point we have not established the nomenclature, think of it this way. Say we're using SHA-I as a hash function. So for SHA-I, the probability of success would be 1 over 2 raised to power 160. In other words, if Eve tries to brute force their way into this encrypted message, the success rate would be very low. Before we dive into the mathematics behind OAEP, let's understand a few nomenclature that will help us in understanding the discussion that's yet to come. We'll use n as the modulus in this RSA encryption, and k is the size of this n in bytes. We'll use an optional string called L. The string is optional, and we'll compute the hash of this string, hash of L. In this example throughout, we'll be using SHA-I as an hash function. So let's say we compute the SHA-I of this L, and this is called L hash, the thing that we have mentioned right here, the first block of the data block. Now, the length of the L hash is hlen. At this point, you might be wondering, but hey, wait, SHA-I is insecure. It's not collision resistant. But you need not worry about that bit. And we'll see in a while that why SHA-I or MD5, as a matter of fact, is secure to be used in OAEP. For quick hints, it's only used as a delimiter. Now, we're using a mask function called MGF, the mask generating function, and it's represented as MGF of L, comma I. What that would mean is I'm asking generate a mask of L byte length from the given input I. So in this context, we say given an input, given a length L, find me an MGF that is taking input as seed. In this context, I'd say find me an MGF, find me a mask, as a matter of fact, find me a mask of length, say L, given the input this masked dv. Now that you are well equipped with the nomenclature, let's dive into the mathematics behind RSA OEP. The first step is to construct the data block. We first pick a random string of called seed of length hlen. For example, if you're using SHA-I, hlen would be 20. Then we say that the seed consists of 20 random bytes. Now, the data block itself would be of length k minus h len minus 1, and this makes the padding string of size k minus m len, which was the length of the message, times minus 2 times h len minus 2. We have two delimiters, 0, 1 and 0, 0. One in the data block itself and one in the final encrypted block, the encrypted message. We use hash functions twice, once in the seed and once in the data block itself. The message length is used once, and k is the total length of the encrypted message. That is how we find the length of the padding string. Now, we will generate a mask for the data block. The DB mask can be computed by saying mgf of seed, comma, we specify a length. The length is k minus h len minus 1, which is the length of the data block itself. We say that generate me a mask of this length using the seed as an input. At this point, we are ready to generate the masked data block. We'll compute the XOR between the data block DB and the DB mask that we just created. And this will give us the masked data block. This step will scramble the DB with the random seed. Next, we'll produce a mask for the seed itself using the mask generating function, or MGF. We say, give me a mask of length h len, taking as an input the masked DB itself. This step simply ensures that the seed is not left in the clear. Now we're ready to combine the original seed and the new mask with an XOR operator. And that will give us the masked seed. The seed is also scrambled at this point by the data block. Now we are ready to build the final block. Simply concatenate everything into a k-byte string. We'll use the 00 starting bytes. We'll use the masked seed and the masked DB. When decrypting, the process is reversed. The recipient uses their private key D to compute C raised to D mod n, and they recover the encrypted message. They can then split it up into 00, the masked seed, and the masked DB, and use the same MGF that we use here and the same hash function, in fact, to unravel the XOR in a reverse order. Finally, they'll check if the hash at h dash, recovered hash, matches with the expected hash and the block contains the same proper structure. This structure. If any check fails, the padding is invalid. Only if everything checks out, the message M is returned. The result is that an invalid ciphertext will almost always be detected and rejected without giving an attacker any useful information. Remember from our conversation before, we can't directly encrypt the string. We need to convert this to an integer primitive. And for that, we'll use our OS2IP formula. Once we have that integer, we can simply use the RSA encryption mechanisms and compute x raised to e mod n. This is how OAEP works. Remember earlier in our discussion, we mentioned that using SHA-I or MD5 is perfectly safe in case of OAEP. Let's understand why that's the case. In OAEP, we use hash function for two operations. One is label hashing, and the other is in the MGF. And in RSAs, it's mentioned as MGF1. Let's take the first case. The hash function is used to compute a fixed length hash of an optional string, L. And even if this hash option string is empty, we always get a hash. Now let's see why that's safe in this context. The hash that we call L hash acts as a domain separator. Its job is to simply to ensure that the label is correctly associated with the ciphertext during decryption. As long as the label is chosen wisely, that is, it is not built from adversary controlled paths, collision resistant isn't critical here. For the mask generating function, the hash is also used there. It's used inside the mask generating function to create a pseudo-random mask. This mask is applied to both the data block and to the random seed used in the encoding process. In this context, the hash function is treated as a random oracle. The job is to spread the randomness of the seed across the larger data block. For this purpose, properties like length extension or collision resistance are not relevant. What matters is the output appears random, and even SHA-I or MD5 can deliver that. This is the primary reason why non-collision resistant hashes such as SHA-I or MD5, which have been proved non-collision resistant, are perfectly safe to be used in OAEP because they are not used in a context where they are required to be collision resistant. Early RSA signatures suffered from the similar problems as raw encryption. Their deterministic nature made them prone to forgery and replay attacks. This vulnerability paved the way for an improvement, the Probabilistic Signature Scheme, or PSS. Towards the end of 1998, Belair and Rugwe also proposed a scheme to overcome the inherent limitations of deterministic RSA signatures. The core idea was to introduce randomness into the signature generation process so that even when signing the same message M twice, the resulting encryption would be different. The randomness comes from a salt value, S, and the carefully designed encoding process. The result is that the signature method is strong and has provable security guarantees. On a higher level, let's try to understand the setup of this signature scheme. We start by selecting out M as the message or the signature, and we compute the hash of this block. We store it as M hash. We pad the M hash block on the left with a padding string PS and a salt value to the right. We again compute the hash of this block M dash and call it H dash. Now, for our data block, we select another added string PS and a salt value, the same salt value S. We may also have a delimiter here as 0, 1, and that is masked by a mask that's generated with the MGF, the mask generating function. And the mask generating function takes input as H dash. So it's saying, create me a mask of length L from the given input H dash. This is the masked DB here. We may also have the ending string in hex 0xBC that denotes that the encoded message EM has reached its end. This is by construct. Now let's dive into the mathematics of PSS. Before we dive any further, it's important we understand the nomenclature that will help us in our discussion up ahead. In PSS, we'll use N as the modulo for RSA encryption. We'll say the size of this N is K in bytes. We'll be computing a hash of the plaintext, M. And the hash that we'll use in our sample example is the same as we used before. It's SHA-I. So we say we'll compute the hash of M, and that would be M hash that you see here. The length of this M hash is HLen. Again, we'll have a mask generating function that will take as input the hash of this whole block over here, H dash, and it will create a mask for the data block. The data block would be called as masked DB. Now that you're well equipped with all the notations, it's time to dive into the mathematics. The first step is to create the hash of the message and a salt generation. So we'll compute the hash M hash as hash of M. In this case, we're using SHA-I. And we'll also create a random salt S of a fixed length, say 20 bytes, if you use SHA-250, SHA-I. The next step is to encode the hash with the given salt. The step is called PSS encode. We'll construct the data block by combining the padding with the hash and the salt. The padding is a sequence of zeros that just fills up the space up to a fixed length. Mathematically, we say M dash is zeros of fixed length and then padded with M hash and the salt that we generated right now. Now, we compute the hash of this M dash block and store it as H dash. We'll generate another padding string PS and concatenate it with a delimiter 0, 1 and the salt. The length of data block at this point is EM length, where EM length is the target encoded message length for the whole block, minus the H length, which is the length of hash, minus 1. Now, we compute the mask as MGF of H, comma, EM length minus H length minus 1. This 1 comes from the delimiter. The H length is the length of the hash itself, and the EM length is the target length. We say that generate me a hash of this byte long, generate me a mask of this byte long using the hash that we just computed. Now, once we have the mask with us, we can simply XOR it with the data block to get the masked DB. Once we have the masked DB itself, we append the trailer field BC, 0xBC in hex, and produce the encoded message. Once you have the encoded message EM, the RSA signature is produced using the RSA private key. But first, we need to convert this to convert the octet string to its integer representation using the OS2IP formula that we discussed before. And then we can apply the RSA private key operation, which is m raised to d mod n, where n was the modulus that we chose in our first step. At the receiver's end, when any recipient wants to verify a signature, they can reverse the process. It is s raised to e mod n, and once they have m dash, the verifier can then extract the components, masked db, the trailer, the hash h, and the trailer, it's bc. They can then recompute this h dash from the message and the salt. The verifier confirms if the hash and the salt embedded in EM, the encoded message block, matches what is expected. If everything checks out, the signature is valid. And that is how PSS works in action. Remember, in RSA, we start out by selecting two large primes, P and Q, and then we compute the product of these two large primes. In the year 1994, Peter Shor demonstrated that a quantum computer can factor out these two large integers in polynomial time, thereby effectively breaking RSA's underlying hard problem, the difficulty of factoring. Although experimental quantum computers have made progress, they remain far from having the required number of qubits, the required stable qubits, to break the RSA key of practical sizes such as those of 2048 or 4096 bits. As of today, there exist post-quantum algorithms such as lattice-based algorithms like Crystal-Kyber, code-based algorithms like Michaelis, and even hash-based algorithms. They are proactive. They're designed to secure our communication well before quantum computers become a real threat. Once RSA is broken by quantum computers, much of the subsequent cryptographic development may be reactive as we respond to unforeseen weaknesses in the new algorithm. However, today's proactive post-quantum research is designed to anticipate these challenges and build reliable alternatives. This video draws inspiration from a variety of sources, including the various RFCs mentioned for the primitives, and the various papers from the authors Rivest, Shamir, Alderman, Silverman, and Bleichenbacher. The complete list of references is provided in the description section.